Okay, so thank you for being here, and so as you can see we are at 55, so I will give you a quick introduction of the company. The company was created 8 years ago by ex-Googler based on the idea and the understanding that for brands today it was more and more difficult to have knowledge about their clients because there was a lot of different touch points in order to get in touch with those clients. But at the same time, there are many available sources of data. So there are, for instance, analytics data coming from web navigation. There are also data coming from many different sources and many techniques in order to leverage the data in order to personalize your marketing. So for instance, the kind of data we can work on are digital data, sales claim data, advertising data, or any source, any external data. And the goal will be the objective 55 to leverage all this data in order to help our clients to build a superior brand experience and to achieve better marketing objectives thanks to this data. We work for many different brands, so from different industries. So it can be automotive like Renault, or bank company like BNP, or retail, or insurance, or e-commerce, etc. So we work with any kind of clients. And our strength is that we have a triple expertise because we have three kind of competence, let's say. So there are main consulting parts of 55, but also strong experts on analytics and media, and a more technology part with some engineer and data scientists. Today we are more than 200 people, and we are present in 5 different countries. So we have offices in New York, London, Hong Kong, Shanghai, and Paris. So that's it for the quick introduction of 55, and I can now introduce you the other presentation. So we talk about multi-task DPP, and I just renamed it yesterday to tensorize DPP, but that's the same thing. And so I'm going to talk about basket completion. So I don't know if you're familiar with the objective of basket completion. The goal is to recommend one or several products to a user in order to for him to buy during a given session. And so we're going to look at the products that is already in the basket of the user. And the idea is to find at least one product that is relevant to show to the user in order to increase the size of the basket and so to increase the value of the user. So in state of the art, there are mainly two approaches today, and the most known one is based on associative classifier, the historical version. The idea is to compute confidence and several rules based on the support of the basket and association between products. So for instance, we can compute confidence or lift score as are written on the slide. And then when the human has to choose different thresholds to say, okay, if this product has a support that is sufficiently large enough, if the confidence that this product may be buy with this basket is high enough, if the lift is high enough, etc., we can say, okay, it's a good idea to recommend this product to the user. So you can see it's not an optimal algorithm because there is a lot of manual decision. We have to choose very different thresholds. And also, if one product is, and there is one new product in the catalog, we have to recompute all the rules, and so it's not very feasible with very large catalog and e-commerce application, and we have new products coming every day, and so those methods don't scale when we have a large catalog. So hopefully there is a second kind of algorithm that emerged the last 2 or 3 years, which is based on determinantal point process, so DPP. And a DPP is a probability distribution that is computed through kernels. So we have a kernel which has the size of the catalog, and so it's a square matrix, right? And so if we want to know the probability that a set of items will be bound together, it's defined by the determinant of the principal submatrix. So for instance, if this is the set of products A, and we look at the row L, the row A of L and the column A of L, we take the determinants, and this will be proportional to the probabilities that this set will be varied together. So there are several advantages to use DPP for this task. The first one is that we have p squared if we note p is the number of item coefficients, whereas the size of possible set is 2 to the p, so it's exponentially with p, and we have a predictive number of parameters. So that's a good thing. Then we can see also that the entries of the matrix will contain the similarity between items, and by construction, the determinants will enhance diversity in the set, which is a good thing to have in basket completion because we don't want to recommend two similar items. So we can see that this diversity by looking at a very simple example when we only consider two products, and we see that the determinant will be L11 times L22 minus L12 squared. And so we can see that the first two terms, so L11 for instance, can be seen as the popularity of the item, and the term L12 is the correlation between item 1 and 2. And so since there is a minus sign, if the two products are very similar, this determinant will be smaller, and so the probability to observe those two items will be smaller. So we see we have an intuition here of the diversity in DPP. So in order to learn the DPP, a common assumption that has been made by Mike Gartrell from FICO is that this matrix is low rank, and so it can be formulated as VB transpose. And then we're going to want to learn this matrix V by looking at historical basket in order to learn this probability distribution. And so we do that by maximizing the log likelihood. And so we have a good estimation of this kernel, and now we can do our recommendation by looking at the probabilities that a given set of items is going to be held together. So there are several advantages of this approach. The first one is, since we have a low rank approximation of our tensor, we have a low memory and fast prediction. So it's really easy to compute prediction, and it's scalable to very large data sets, which is something we want to have for basket completion. Otherwise, there are several disadvantages. The first one is that by construction, if we have a set of items which is larger than k, which is the rank we assume for our kernel, by construction the determinant will be 0, and so this set will have a probability 0 to be votes, which may be something difficult when we have a problem when we have large baskets. The second one is that we don't really model the probability to buy an additional item, but we only model the probability that the set of items is going to be bought together. So in order to solve the issue, we propose several modifications of this algorithm. The first one is that we are going to learn one kernel by item we want to recommend. So we're going to have p different kernels. Then we're going to add a diagonal matrix, then we capture the bias apart from the first part of the matrix. So it will help not to have a determinant that worth 0 if we have more than k items in the basket. And now we can see that we have a cubic tensor because we have all the different kernels. And since we cannot learn one kernel per item, you're going to assume that this tensor is low rank. And then we're going to add a logistic-like function on top of this kernel to predict if yes or not this particular item will be bought when those items are seen in a basket. So to be more clear, for a given target item tau, we're going to have this kernel to learn. So we see that we have the d-square matrix that I was talking about before that captures the bias. And then we have a middle matrix, V R2 square V transpose, and the R2 square will capture the embedding of the target item we are willing to recommend to a user given the items that are in the basket. And then with the logistic form, we can directly compute if yes or no it's a good idea to recommend this item. We made several experiments in order to validate these new approaches. So there are 4 datasets. So there is Amazon dataset, Belgium retail dataset, UK dataset, which is all retail and online datasets of people buying a different item during a given session, but there is no notion of ordering, so we don't know in which order the item has been added to the basket. And then we have one dataset, so in the Instacart dataset, where we have this information. So this dataset will be very helpful in order to check if there is information in the order in which the items are added to the basket. So I will only focus on the Amazon dataset and the Instacart dataset. And there is two sub-experiments in the Amazon dataset. The first one only on the diaper category, and the second one on 3 disjoint categories. So by disjoint, I mean that if someone is buying products in the diaper category, we will never see a product from other categories in this basket. So it's completely disjoint, and that can be an issue for some algorithm. In order to test the performance of the algorithm, we're going to have a training set when we keep only 70% of the basket. And for the remaining basket, we remove one item at random, and we're going to try to predict, to decide what to recommend to the user, and going to check if this item was actually recommended to the user or not. So here we remove one item at random because we have no notion of the order in which the item is added to the basket. In the second type of data, we're going to have 3 protocols. So the first one, we do the same, we remove one item at random. The second protocol is that we remove the last item that has been added to the basket. So if we compare both approaches, we can check whether or not a given algorithm is able to predict correctly the last item and not only one item at random. And then we have a third experiment, only for the tensorized approach I just spoke about before, where in the training set, we remove one item at random, and in the test set, we remove the last added item. And so here we can see if the model is able to generalize, even if it didn't learn appropriately the right task. So we compare with several baselines. So we have different versions of our algorithm. On the details in this different version, but we can ask about it later if you want. And then we have several baselines. So we have Poisson factorization. We have a factorization machine, which is classic collaborative tutoring algorithm. We have a recurrent neural network. And we have our baseline, which was the Romain DPP and the Bayesian version of the Romain DPP, and also the associative classifier. In order to measure the performance, we're going to focus on the mean percentile rank and the precision at k. So what are those two measures? We're going to remove one item, as we said. We predict the probabilities that one item will be bought given a basket. We sort all those probabilities, and for the NPR, we just compute the average percentile rank of the actual item we removed, and so the higher the better. And for the precision at k, we just look at in the top k if the item we removed was actually in the top k recommendation. And so likewise, the higher the better. So in the first experiments on the Amazon diaper dataset, we can see several things. The first one is that the associative classifier has poor performance and is close to and even equal to random prediction. We have the same with Poisson factorization. Maybe the problem comes from the fact that the baskets we observe are very small, and so we don't have enough information in order to fit appropriately the parameter of the factorization of the matrix. And we see that in our multitask version, so that should be a tensorized version, when we remove the matrix D, so the bias, we have almost the best performance. We are really close to the final version. So we see that capturing the bias in a separate matrix just gives an extra push to the model. But the main thing comes from the tensorized version, where we directly can understand how products are already added in different order in the basket. And we have similar results on the 3 categories datasets with even higher performance, because our tensorized model was not hurt by the fact that the categories are disjoint, whereas other models have trouble to understand efficiently that those categories are disjoint. Finally, we can look at the order datasets. So I write below the 3 protocols. So one at random, last added, and like a hybrid version. So the first thing is that we can focus on the state-of-the-art lowering DPP algorithm. We see that the two performance are quite close, except on the MPR when we try to predict the last item, we lose like 15 points in the MPR, which means that the model has trouble to predict the last added item. It understands global covariance of the sets, but not the last added one. Whereas when we look at our version with the tensorized version of the DPP, the best performance is obtained when we try to predict the last added item, and there is a difference when we learn it by removing one at random or removing the last item. It means that there is a real information in the order in which the item has been added to the cart, and that, to the best of our knowledge, that's the only algorithm that appropriately captures this information, because it really have a better performance than the other algorithm, even if the RN algorithm. So to conclude, I present extension of the low-rank DPP model in order to tackle the problem of basket completion. This algorithm can also be efficiently learned by mini-batch recommendations and using some parallelization techniques. And also, thanks to this low-rank approach, it can be really scalable to very large catalog, which is something very desirable. So thank you for your attention, and I'll be happy to answer to your question.
I was wondering, when you said that the basket you use a rather small size, have you tried with your method to increase to some really bigger size, like 1,000 items?
Yeah, it's quite rare that the baskets are that large, because usually people used to buy 100 items at the same time. But there is one dataset, which is this dataset, so the UK dataset, where there were more than there were some baskets with more than 100 products. So the thing is, I had to cut all the baskets containing more than 100 products for the competitors, because for the low rank, I would have to use like a low rank of size 1,000 in order to capture all the baskets. So just to compare with this algorithm, I just cut at 100, and I use a number of Latin factors of 100. And so we see that, again, the tensorized version got the best results, except on the MPR, but I don't know why the MPR is lower. But on the other metrics, we have a 30% increase on the precision compared to the low-rank version also. But that's the only dataset that contains like more than 100 products. And for the other one, so the Amazon, it was around 2 and 3, for the Belgium around 10. And so here the mean is 19, but there are some baskets with more than 100. And for the Instacart, it was like around 10 products, because it was a grocery supermarket, so it's around 10 products in the basket.
Could you explain quickly what is a multitask version?
Yeah, actually that's I should have renamed it tensorized all along, and that's multitask. That's a last minute change of the name. The idea of multitask was here. It says that one task is this: is this item a good idea to recommend or not? It could be seen as one task, and we want to do that for all the items. So we have multiple tasks, and so at first I call it multitask DPP, because what I want to do next is that not to use not only this algorithm for basket completion, but for other classification problem, and to use the DPP in order to learn this classification problem. And so in my head it was to generalize later, but multitask tensorize, it's the same for now.
Did you have the opportunity to try this new algorithm in a real-life case, or not?
Semi-real life, because that's the same. We have proprietary data at 55, and I use in offline the model in order to test the model, but never because it was a very recent job, and so it's not in production yet. But I keep you posted when it's in production.
To follow on this question, so it's not ready yet, but do the results are promising, and you are going to push it in production, or you have to work on the method?
Yeah, because actually, when I first was aware of this method, we tried to push it in production, and we have a near production version of this algorithm. And then I worked like the last few months on this tensorized multitask version, and so we saw that it gets better results than the method that we were used to. And so now the next step we need to test that. And so we have several kind of application, but not only for basket completion, the idea of item, but we are working with a mall company, so they have malls and multiple stores, and so the idea would be to recommend stores for users to visit during a given day, and so it's also a good idea to do basket completion like algorithm. It's not purely collaborative filtering, but because you may end up in recommending a store that you may like, but not today, because today is in a different state of mind and guiding something very precise, and so it's not in the journey. Okay, thank you. So